In the previous lecture, we discussed about the SIESTA input file, how to write, how to mention all the required parameters for different properties calculation. So, in this lecture, I will show you the SIESTA output file, what it tells us regarding to the input file. So let me show you first what is that. So here you can see that vi silver dot out. So let me make it a little bigger so that you can clearly see the information what it has. So okay, so when you open the SIESTA output file, so here it shows SIESTA version and architecture, compiler, GNU for RAM, and compiler flags and libraries. Here you can see that in this line it is showing that serial version is basically installed. So and this SIESTA is working in serial mode. Okay, serial mode means that one processor at a time only it can use. Okay, so here we just go welcome to SIESTA, and these are this is uh, all this is about uh, the input parameter which we gave it. Okay, so here you can see number of species 1, number of atoms 4, and chemical species label, and pseudo atomic orbital basis double zeta, and here you can see that the latest constant is 1 and we place the latest vector as it is. So here you can see that A and A equal to B equal to C. So this is the cubic structure it gives us, and this is R. Okay, so here the input file is completed here. In here you can see end of input data file, and from this below here is now is the simulation data is shown. So here species number is 1 atomic number, and 47 is the atomic number is 47. So label is silver atomic symbol, which means okay here. So all information when it reads the input data file, so it gives at the after that it gives us the summary of the input file, that what kind of information actually we are looking for. Let me show you. So here you can see here it is the summarized form. There's a simulation parameters which we mentioned in the input file. So the following are some of the parameters of the simulation. A complete list of parameters used, including default values. So CSI can be found in file out.fdf, and here you can see that spin configuration is, because in this calculation we do not use spin polarization, so it is none, and number of spin components is 1. Okay, so spin spiral long output is you can see here true. Okay, and charge density information will appear in the dot file name dot rho row, which is row is, you guys know that row is density actually. So here it gives us all the that such kind of thing. Those which parameters in front of which f is written, that means it will not be calculated by default because we do not change that. And the one where it is written t means true and f means false. So it is all about this. So here you can see this is all the parameters. Okay, we apply the conjugated gradient method. Okay, and the variable cell you see here, the variable cell is true, and use continuation file for CG files. So here we can. So here the summary of this file is completed, and after that now the simulation is started. So here I want to show you, this is step 1. Step 0, so step 0 means the coordinates, the position coordinates which we placed or which we wrote in the input file. So basically that is the 0 position. Okay, so here you can see. So for that position, you people know that we mentioned in the input file this parameter a, b, c. Okay, and after this, it will give us the energy of this position. So here you can see. So the coordinates which we place in the input file has the total energy of minus 3929.63 is electron volt. Okay, and now so this is minus 3929.63, and if we go to the end of this file, shift G, with shift G I can go to the bottom at the end of the this file. So here you can see, you see here the total energy in the initial step is minus 3929.63 it was, and now it is minus 3936.56, which means that this energy is basically the lowest energy. And here, and initial energy is the that shows that the geometry or the structure we took for simulation purpose was in high energy state, and during, after optimization it comes to the ground state energy. So let's go a little bit up, uh, where it is here it will be written that the geometry is relaxed or not. Okay, so let me start this slowly. You see here, relax atomic coordinates. This means that our geometry is at the ground state now. If this is not you, if you cannot find this line in your output file, that means that your geometry is not in the ground state energy. So you need to rerun again the simulation from that point. Okay. So this is one thing. And here you can see that what kind of file it created. So you see a number of files it created. Okay. So those output file, which is we mentioned in the input file. So look at here. Here. So here you can see that this is our system level silver bulk. Okay, this one. This silver bulk, if so in the directory you see the file name with this one, so that means that these are the output files created by the mm, uh, simulation after completion of simulation. So here you see silverbulb.ani, silverbulb.bib, silverbulb.bonds, and all these things. Okay, so let me visualize this ANI file. So I will show you here in the VMD. I will open this file, and here. So I just copy that ANI file only from the uh, Ubuntu, and here I will give it file type is XYZ. So here you can see. So this job is, you see here, here it shows 7 frame. So this means that this job, this geometry is uh, this geometry is basically optimized from the high energy state to the ground state. This energy comes in the in 7 state. It comes to the ground state energy. So let me show you this CPK. So here you can see, and in the display I will click the orthographics so that the structure becomes clear. Okay, here you can see that these ball types are not really spherical, so I will increase the sphere resolution. So as I increase, you can see the sphere is clearly well in symmetrical sphere. Okay, so anyhow, when I run this job, because these number of steps are very small, optimization is quickly came. So here you can see I will just click by one by one. So this is step one from 0 to 1. So okay, just look at here. This 0 means that this is the geometry which the coordinates which we place in the input file. And when it starts simulation, so in the first step, the geometry is expanding. You see, again, it's contracting, expanding, expanding, contracting, expanding, and finally, the geometry is relaxed. Okay, so this is all about the uh, optimization process. So let me show you my own work so that you can see that how long the geometry optimization can be. So computational data. So let me check here the ANI file. Okay. So here, from here I will take the ANI file. Where is the ANI file? Now let me check. Okay, here. This is the ANI file. Okay? So this file I will bring it here. I'm just showing you that I don't remember that how long this geometry is. But here you can see this geometry may be optimized and uh, maybe, because I'm not sure, I need to check it properly. But anyhow, here it shows 107 frames, and this geometry has 208 atoms. So if you look at here, so let me run the movie. So here you can see how this geometry is interacting with the surface. If I make it fast, so here you can see. Do you see? Okay. So this is all about how we can visualize that how this structure is making bond with the structure. Okay. So this is. Let me check what else I was showing you. Okay. So this is all about the simulation output input file. Okay, let me show you. Yes, I remember. So let me show you the output file vi silver.out. So we know that here you can see that the latest vector is 4.0857, and whether the geometry is the variable cell expand or contract. So let's check it. Uh, Here you can see. So this is okay. Here it is written the relax atomic coordinates, and you can see that the variable when we kept the cell variable, so the volume uh, uh, instead of expanding, it contracts. Here 4.14, sorry, it expanded because that is 4.0857. So the cell is expanding 4.144 and 4.144, and here you can see that the x have three coordinates, x1, x2, ax1, ax2, ax3, and here bx1, by1, by2, by3, and the same is cz1, cz2, and cz3 here. Okay, so the cell variable means that this cell is basically expanding. Okay, so this is all about today's lecture. Thank you so much.